Today we're going to talk about intros to GPUs. So first of all, why do we need GPUs? In order to convert a 3D world into a 2D image, we need to do some math. The most fundamental part is the perspective projection. The points in 3D space need to be mapped to a 2D plane based on how they will appear to a camera. Texture also has to be applied, as well as any lighting and other effects. This can all be done in software by your CPU. And in the early days of graphical applications, it was. However, it turns out that CPUs are not perfectly suited for this task. CPUs are good at executing one thing very fast. As far as parallelism goes, most consumer CPUs can only execute about 4 computations in parallel. Operations on vectors and matrix multiplication, however, can be massively parallel. The position of one vector in space isn't dependent on the position of other vectors, so you could in theory project the entire scene at once given enough parallelism. And this is why we need GPUs. So what is a GPU? GPU stands for Graphic Processing Units. The GPU is manufactured using the same technology as a CPU. However, it is built for parallel graphical applications. Early GPUs use a fixed function pipeline, in which graphical programmers send vertices and textures to a GPU, sets up a few options, and the GPU did the rest. However, graphic programmers wanted more flexibility, so modern GPUs are more programmable. Vertices and textures are uploaded to the GPU, and a program executed by a GPU defines what operations are performed on the vertices. These programs are called shaders, and there are 2 main types of shaders. Vertex shaders run operations on vertices. These are often used to perform the 3D to 2D projection, as well as translation, rotation, and scaling plot objects. The other main type is fragment or pixel shaders. These shaders operate on output pixel and map a pixel on a screen to a color. This means that these shaders are where textures and lighting operations happen. So how does a GPU work? A GPU is like a CPU in principle. It executes instructions on inputs to produce some output. The main difference is that GPUs consist thousands of parallel cores rather than just 4. The NVIDIA RTX 2080, for example, contains 2,944 cores. Each core runs the provided shader on a given vertex on pixel. Since it can be done in parallel, this provides a massive speedup over the same operations on a CPU. So why ever use a CPU? While GPUs are really good at parallel processing, CPUs can still be better for serial processing. In particular, while GPUs have thousands of cores that can run thousands of threads simultaneously, CPUs can only run a few threads at once. The cores in the CPUs are much more powerful than the cores in GPUs. NVIDIA GPUs contains cores that implement the CUDA artifacts. Compared to a CPU core, a single CUDA core executes instructions at a slower speed due to architecture differences such as having a smaller cache and slower clock rates. In general, GPUs are optimized for throughputs, while CPUs are optimized for latency on a single operation. Additionally, CPU cores are smarter than GPU cores, in the sense that they implement a larger instruction sets than CUDA cores, because they need to be able to perform operations for things like I/O and interrupts that GPU doesn't support. CPUs also are designed to support more robust full control and memory management. For example, not all GPUs cores support recursion on virtual memory. These design trade-offs makes it so that GPU cores requires less memory and far fewer transistors than CPU cores, in which is why it can be cost-effective for GPUs to contain so many cores. However, GPUs cannot be used as the main general-purpose computing units on a modern computer. They are still very good at graphics processing and machine learning though. So what type of tasks are GPUs and CPUs used for? In general, GPUs excel at tasks that involving applying the same computations to different pieces of data parallel, while CPUs are better for applying different operations to the same piece of data serially. It turns out that lots of image processing tasks are extremely parallel. For projection and shading computation, each vertex or pixel can be handled in a single thread, enable far better performance using GPUs. Generally, GPUs are really good at matrix calculations, where individual entries in a matrix are computed on a single core, in which is also why using GPUs can provide a performance boost in machine learning applications. And what is the future of GPUs? Broadly speaking, GPUs are going to get faster and more cost-effective over time. Moore's law states that the number of transistors in a single chip tends to double every 2 years. Both GPUs and CPUs has been following that trend for several decades. However, it might change by the year of 2036. And in summary, GPUs has more cores, they're good at parallel computing, and graphics tasks can be very parallelized, and that is why we use GPUs for graphic processing tasks.